OK, so what are the useful properties, right? Now that we've put out of the way the thing that we cannot compute anything, this thing's infinite, it's kind of slightly awkward, there's actually some really nice properties. The first one is that if I take a Gaussian and I do what's called an affine transformation, all right? Affine transformation. That just means I multiply my random variable by a scalar, a number, and then I add another number, OK? So if I do this simple transformation, so it's taking a function, but it's just like a function whose graph looks like a line rather than something nonlinear, then what I get is that this thing is also a Gaussian. Nice, right? I start with a Gaussian, I take an affine transformation, I get another Gaussian. Now if I take a Gaussian, I square it. This is not going to happen just because the square of the random variable does not allow for infinitely negative values. So this is not the case for any transformation, but affine ones do work. And what we get is that the mean is going to become a times mu plus b. OK, so that's just linearity of expectation. The expectation of this quantity is a times expectation of x plus b. So it's a times mu plus b. And translation is not going to do anything. Like adding this b is not going to do anything to the variance. So the variance is just a squared times the variance of x. And so that's a squared sigma squared. OK? And here I really used nothing to write those two things. I used linearity of expectation and the property of computing the variance of such a thing. The thing that I told you that is new or supposedly new is that this is still a Gaussian. OK? And that's not always the case. If I take an affine transformation of a Poisson random variable, or a Bernoulli random variable for that matter, right? I don't get a Bernoulli random variable, okay? Because Bernoulli is, the minute I multiply it by something, I don't have support 0, 1 anymore. So, this is a nice property. We don't really use that very much. The way we use it in a way is to say, I want this guy to be 0, and I want this guy to be 1, so that I actually can find, at the end, a standard Gaussian random variable. So we're looking for a and b such that this will happen. And the way you do it is by saying, OK, if I start with x, which is mu sigma squared, what I'm going to do is I'm going to remove the mean. That certainly makes sure that this new random variable has mean 0. And then I need to multiply it by a number so that the variance is 1. And so this number is 1 over sigma. So if I do x minus mu divided by square root of the variance, also known as the standard deviation, you can check that in expectation, this thing is 0, and the variance is equal to 1. And we know from this guy that this is also a Gaussian. So this process is called standardization or normalization. This quantity is sometimes referred to as the z-score of x. And this is the way that we actually, the reason why we do this is because if we want to read something about tables, it's not very convenient to have a table for every possible value of mu and every possible value of sigma squared. But we can actually have only one table for a standard Gaussian and go from any Gaussian to that guy. OK, and that's how we're going to do this. So now if I want to compute, for example, the probability that some Gaussian x with mean mu sigma squared and variance sigma squared is between two numbers, u and v, all I have to do is to remove mu and divide by sigma on all three members of this inequality. So, sorry, x minus mu divided by sigma minus mu divided by sigma. So we know that z itself is x minus mu divided by sigma. And so now all I have to do is to compute the CDF of z evaluated at this guy minus the CDF of z evaluated at this guy. OK, so we go from computing probabilities about x to computing probabilities about z like that. OK, so that's the purpose of standardization. Now, another property, if you go back to looking at what the standard Gaussian distribution looks like, it's symmetric, right? It's completely symmetric about 0. It's an even function. And that means, that the distribution of x is the same as the distribution of minus x. If I had a mean which was not 0, this would not be the case. It would be that the distribution of x minus mu is the same as the distribution of mu minus x. But when it's about 0, it's fine. The variance itself does not matter, right? This distribution or that distribution are both symmetric about 0. And why do I mention this? I mean, it sounds like a silly observation. Is because now if I actually look at the probability that absolute value of x exceeds little x, and this is precisely the kind of stuff we wanted to compute, remember, right here? Probability that absolute value of some Gaussian with mean 0 and some variance exceeds something. The absolute value was something that we put in because we said we want to find the absolute deviation of Rn to p. We don't care whether it's positive or negative. So we're going to have a lot of those absolute values coming in. And so we're going to need to compute the probability that absolute value of a Gaussian exceed little x. And so the way we do it, we say, OK, what is the probability that the absolute value of x exceeds little x? Well, either x itself is larger than little x, or minus x, minus capital X, is less than minus little x. Agreed? So this is the probability of a union, but those two events are disjoint, so I can actually say that is the sum of the probabilities. So I'm going to write it as the probability that x exceeds little x plus the probability that that x is less than minus little x. Everybody agrees with this? This is just basic probability rules. I sort of hid in there the fact that the first step is that this is the probability of the union of this event and that event. And then I say that the probability of the union is the sum of the probabilities because those two events are disjoint. And this is one of the basic rules of probability. OK? And now, what I claim is that since minus x has the same distribution as x, I can actually put a minus sign here, put a plus sign here, and here I actually need to change my inequality. Okay, so that's the probability that capital X exceeds little x, probability that minus capital X exceeds little x. But we just said that minus x has the same distribution as this guy. So those two probabilities are actually the same thing. So this is equal to 2 times the probability that x exceeds little x. So when we're going to have absolute values, we're going to break it, and there will typically be a 2 that shows up. OK? Is that clear for everyone? Now be careful here. I used implicitly the fact that little x was positive. Any questions about this? The basic rule of probability, and plus the fact that we have a symmetric random variable.